Now let's do an example. Let's do the slotted line example 2-5 on page 60 of your textbook. This was done in the classical way in the textbook, and let's look at how to do this with a Smith chart. This is a problem where you are given the location of the voltage minimum is 12 centimeters. The voltage standing wave ratio is 3, and you want to find the load impedance. So the first thing that we're going to do is plot the voltage standing wave ratio of 3. Well, right here is the value of 3, so we can see that the voltage standing wave ratio right here at 3. Now let's just use a protractor or my piece of paper, and let's draw the voltage standing wave ratio of 3 kind of going around like so. It's basically a circle like this. That's the voltage standing wave ratio, VSWR equals 3 circle. Now let's find the location of the voltage minimum. This axis right here is the L-min axis, so this point right there is L-min. Let's see how far away that is from the load in terms of wavelengths, because that's what we need for the Smith chart. So L-min in wavelengths is going to be 12 centimeters divided by the wavelength, which is 0.6 meters, or 0.2 wavelengths. So if I'm at L-min and I go towards the load, 0.2 wavelengths, I'm going to come to the load. So let's read our value out here. We can see that we are at 0 and we're moving in wavelengths towards the load. So I'm going to go 0.2, see here's about 0.1, 0.15. Oops, let's see, make sure I'm getting these values right. I want to go 0.2 wavelengths. It's right there. Let's draw our straight line from the center out to 0.2 wavelengths, like this, and then I'm going to mark my distance right there on that point. It's right here. That is my load value, ZL. I went 0.2 wavelengths towards the load from the location of the voltage minimum to the location of ZL. Let's read its value. It looks like its real part is about 1.8 and its imaginary part is about 1.2. In order to get this to ohms, I'm going to multiply that by Z0, which is 50 ohms. Now one question that comes up, and certainly it came up here in this picture, is how accurate do you need to be? A Smith chart is not an awfully accurate device. It's not as accurate as calculating this from scratch on your computer, of course, but it gives us a fantastic feel for what is going on in our circuits. So frankly, if you are as accurate as a broad felt tip pen, I'll be completely content. On the exams, what I'm looking for are that you do the steps correctly, that you follow the right axes, that you follow these lines, for instance, these lines and these, and that you go the right directions. The absolute accuracy, pretty flexible on that.